So as stated, so I'm going to present this model. There are two important keywords here. It's non-local and two internal lengths. The question is, why do we need a non-local model? So it is very well known nowadays that if we use standard models, damage model, whatever the model, we get spurious mesh size dependence. Here's an example of a calculation I did with the CT specimen using a GTN model. And I'm decreasing the mesh size, so here I have 200 microns down to 11 microns. And you see that the load displacement curve drops down, and we know that there is no end to that. So there is a need for these non-local models. Something which is maybe less known is the spurious effect of mesh design. For instance, here I'm trying to simulate cut contracture, and I designed a mesh, initial lot 1, with, which is aligned with the load axis. So it's 0 degrees here, and then I'm starting tilting this initial mesh by 5 and 10 degrees. Indeed, there should be no influence of the mesh orientation on the results. What we see here is the load displacement curve is exactly the same, but if you look at the crack path, and we here in red the broken elements, for 0 degree, a standard mesh, we have what we call a cut pull fracture, so that's the center of the tensile bar, a flat crack, and then it deviates to form a slant fracture. And you see that with 5 and 10 degrees, we get completely different crack path, which means that using the standard local models, it is absolutely impossible to predict crack path. Why two internal lengths? So if you look at engineering materials, you very often see two inclusion populations that are at the origin of fracture. Here's an example with a standard aluminum alloy. At high triaxiality, I get fairly large dimples, which are initiated on particles containing iron. At lower triaxiality, and note that the scale bar here is exactly the same. At lower triaxiality, I get much smaller dimples, which are initiated on very small dispersoids that are here to strengthen the material. Here's a second example. It's a 9-pi steel. High triaxiality, I get large dimples, which are initiated on sulfides and oxides. I go to a lower triaxiality, and once again, the magnification is exactly the same. We see much smaller dimples, which this time are initiated on strengthening particles, which are the iron carbides. So after this context, here's the outline of my talk. I will briefly present the Besson-Niedelman model, which I think is very well known, then present its extension to a non-local framework using two internal lengths. And then we will use this model to see the link there is between the internal lengths and the localism bounds we observe in the simulation, and investigate some size effects. So the GTN model is briefly presented here. We have a yield surface, which I can define like that, where sigma f is the flow stress, sigma star is an effective stress, which is defined by solving this equation where you have the von Mises stress, the trace of the stress tensor, Q1, Q2 here, on F star and model parameters. Based on that, we have the plastic flow, which is given by the normality rule. And here we introduce two damage mechanisms. The one which is void growth, which is on the porosity due to void growth is Fg here, and its law of evolution is just given by mass conservation. And there's a second damage mechanism here, which is driven by strain. Accumulated plastic strain is kappa here, and it's strain control nucleation. Here at secondary nucleation, the small particles, so we always assume that you need a lot of plastic deformation before starting this damage process. And here we assume that this is active only when we have a plastic strain higher than 1.2. Remember, it's a model still very tough. Indeed, we are using a finite strain framework, which I'm not going to detail here, but it's indeed very important. So starting with this base model, then here is the non-local extension. We use the implicit gradient model as proposed a long time ago by Pierre-Lins. We have a variable which corresponds to the volume change, which is just the trace of the plastic strain, very tensor. And we consider two sets of local coupled. It's not staggered sheet, it's strongly coupled. So we use a monolithic solver. And it's implemented in axis symmetric, 2D plane strain, and 3D. And we use quadratic interpolation for displacement and linear interpolation for the non-local variable omega bar and kappa bar. So the cost of having this non-local variable is not so high because these are interpolated using linear function, whereas displacement are interpolated using quadratic shape functions. And further of all, it solved the mesh orientation dependence I was mentioning in the introduction. That's a reminder of what I've shown. Here, whatever the mesh orientation, we exactly get the same feature. Flat crack growth and then crack tilting. Whether it goes up or down really depends on the way the problem is solved. And indeed, I will not show an example here, but indeed it also solves the mesh size dependence. Here we are studying the relation between the internal length and the localization bound, because imagine you are doing an experiment, what you measure in your experiment is not the internal length, it's going to be the size of the localization bound. So here, for sake of simplicity, we assume that both lengths are equal, and we define the localization bound width as the width of the damage profile at the location where it's half of its maximum value. And here we are studying volume change, and we have volume change equal to 0.5, which is a fairly high volume change, with very close to fracture. The red profile is the local variable, which is not regularized and which is localized here within one element. What we see, we did the study for plane strain and axis symmetric. Roughly speaking, the localization bound width is about 2 times the non-local size you incorporate in your model. And then you have to worry about the element size that you need to use, because you need to have enough elements within the localization bound so that you can discretize it. So when very close to failure, because elements tend to stretch, very close to failure, the element size must be about 1/3 of the localization bound size, which means about 2/3 of the internal length you put in your model. And these are guidelines for mesh design, and in particular mesh design when we do mesh adaptation. So here in this graph we are playing with both lengths at the same time. So this calculation were not performed because this corresponds to the case where the length associated with nucleation is larger than the length associated with growth. Here both lengths are equal, and here we are increasing, in that direction, we are increasing the length for void growth at constant length for void nucleation. So let's consider this line here. So it's constant nucleation length. We see that when we increase the length associated with void growth, the length of the central part, which is flat, tends to increase. This is also very clear on this line. And in some cases, you see that we only have flat fracture. And it really depends on the ratio of both lengths. Now, for sure, all these calculations were done varying the length scale but having a fixed specimen size. But it's exactly the same thing as changing if you change the internal length, at a fixed specimen size, it's exactly the same thing as changing the size of the specimen for fixed internal length, which can be done experimentally. We can machine small and large specimens, changing the specimen size, but we can hardly change the material length, which are material properties. So that's what I'm indicating by this line here. Oops. Here. So if I go in that direction, the interlag lengths are increasing, so this corresponds to using smaller and smaller specimens. Okay? And it seems that cut cone fracture disappears when the specimen size is reduced. So we wanted to check if that was actually the case, and we did the experiment. It's the work of Shiraz Belaj in her PhD. So we machined both tensile specimen but also notch tensile specimen with different minimum radii, so going from 1.2, which is a fairly small specimen, up to 6 millimeter, which is a regular size specimen. And what you see here in this example is that with a regular size specimen, you get here the central flat fracture and the cup cone fracture around. And here for the small specimen, cup cone fracture completely disappears. You just see dimples and flat fracture. Here we have the intermediate case where we still have a little bit of cup cone, but obviously less than in the case of the standard specimen. So this could, I mean, these are very preliminary results, but this could be one way, changing the specimen size and going down to very small specimen. This could be one way to determine directly, more or less directly, the internal length we need in our models. So some conclusions, which I'm going to skip very fast. So we have the computational framework. The model indeed allows to get rid of mesh dependence. And the use of this model for cracking and crack insertion and remeshing will be presented in the next talk. Improvements will include better control of pressure to avoid volumic locking, which occurs sometimes, and improving the elements using linear interpolation for the displacement to go really into 3D simulation, and indeed doing fully parallel computation. Thank you very much. It was slightly too long, sorry.
Okay, other questions? Yes, please.
Yes. I just need a small reminder, and for the second length scales you are using the nucleation, yeah? It's a nucleation.
Yeah, that's nucleation, yeah.
And what
but once again, that's nucleation of secondary particles. That's not nucleation on the primary inclusion. We always assume that the primary inclusion are there from the very beginning and that they nucleate very early. So we consider the volume fraction of the primary inclusion as voids.
Okay, and now I have my actual question. And what happens if you have shown these different cases where you have this cup cone behavior? What happens if you simulate a CT specimen?
So Amar will show an example, but what do you expect? CT specimen with the parameter I'm using, you see there is no nucleation in fact, it's just void growth.
Okay.
Because it's high triaxiality.
Okay, so nothing's, because sometimes I expect something like that the crack starts to
tilt.
Yeah.
But you need very long crack propagation. But that's exactly, you're completely right. We go back to the aluminium case. So in the aluminium case, this picture was taken, that's a fracture of a sheet. And this picture is taken close to the initiation of the ductile crack, where we have the triangular crack initiation zone. And this picture here is taken where the crack is propagating slant. And triaxiality drops, and you get that. And this possibly can be used to model this flat to slant transition, which is a more complex thing as the slant fracture. It's basically the same thing, because when you have cup cone fracture, triaxiality decreases from the center when the crack propagates towards the outside surface. So hopefully in 3D, we should be able to get flat to slant transition.
Okay, thank you.
But it's difficult.
Okay, thanks again.
Thank you.